In this video, we're going to talk about the last few concepts related to kinetics, specifically catalysts and other factors affecting rate. So the last few topics in AP Chemistry Unit 5. The thing we want to keep in mind as we're looking at what factors affect rate of reactions, and catalyst is one of those factors, is collision theory. So we've learned about the fact that the central theory behind kinetics is that reactant molecules need to collide with each other. Let's keep that in mind when we look at four different factors that are going to affect how quickly a reaction proceeds. The first of those four factors is temperature. And it should make sense that increasing temperature increases rate, because remember, temperature is directly proportional to kinetic energy, right? 1/2 mv squared. And if we have a higher temperature, that means we're going to have more forceful collisions with higher velocities, and we're going to have more frequent collisions. And so we're going to increase the chances of collisions occurring that are effective. As a general rule of thumb, that doesn't apply to all situations, but a 10-degree rise in temperature can double the rate of a reaction. So in the iodine clock challenge we looked at recently, just having a slightly warmer day in the classroom than the day before might significantly change the outcome of how quickly that reaction proceeds. Now, there is a mathematical relationship between temperature and the activation energy. We're going to look at that right now. That was developed by Svante Arrhenius, and you may recognize that name from his theory of acids and bases. The relationship between the rate constant and the temperature of a reaction is given by this equation, and there's a couple of terms in there that are new and some that are familiar. Temperature in Kelvin, R, the ideal gas law constant, are familiar. The rate constant, lowercase letter k, is given there, but the other terms are one called the frequency factor, that uppercase letter A in the equation, and that is a constant that's specific to a particular reaction. And the other is the activation energy. Notice that Euler's number there, the little e, is the 2.718, that mathematical constant that's factored in there. The good news is we won't actually be doing calculations with this equation in class, but we certainly want to understand the relationship between temperature and rate. And you'll notice that mathematically it makes sense that a higher temperature will actually give you a higher value of the rate constant. It's also important to remember that this is the only factor that affects rate by actually changing the value of k. So when a k value is given, it's actually specific for a given temperature. Let's remember the Maxwell-Boltzmann distributions we looked at earlier in the year when we were studying gas laws. The higher temperature, you can see, is given by that red line, and you can see that as a result of that temperature increase, there's now a greater percentage of particles which have that sufficient activation energy. If you remember what happens as you increase temperature to a Maxwell-Boltzmann distribution, the area under the curve remains the same because the total number of particles in the sample has not changed. But you can see as it shifts to the right and becomes more broad in its distribution, you're including a greater number of particles in that red shaded area, whereas the blue shaded area in the bottom corresponds to the percentage of particles at the lower temperature where sufficient activation energy has been reached. That term in the top right, by the way, is a term that's a number between 0 and 1, and it represents the fraction of molecules that have that sufficient amount of energy. So that's the first factor affecting rate we're going to consider. The second one is also pretty intuitive when we think about collision theory. A higher concentration of a reactant is going to increase the frequency of effective collisions because there are just more particles to bump into each other. And we measure concentration, of course, in molarity. However, if we're talking about a gas phase reaction, the equivalent of molarity is partial pressure, and we're talking about the concentration of gases in a mixture. We're going to need to remember that partial pressure is going to have the same effect on a gas phase reaction as molarity is on an aqueous reaction. So higher partial pressure or higher molarity means higher concentration and a higher rate of collisions that are effective. Here's the third factor we're going to consider. which affects rate. So I'll give you a second to figure out what that is. 3, 2, 1. Yes, that's a catalyst. Get it? Sorry, just had to include that. Yes, a catalyst is something that affects rate. So the definition of a catalyst that we'll use is a substance that affects the speed of a reaction without being consumed. And most of the time we're going to assume that they speed a reaction up. Although there are negative catalysts which can actually decrease the rate of a reaction, they're not very commonly considered in AP chemistry. There's a couple of ways that catalysts can work, but it's important to remember that no matter how they work, what mechanism is involved, they are always going to increase the rate of effective collisions, or they increase the number of effective collisions. One way they can do that is by actually introducing a new pathway, like a different reaction mechanism, an entirely different way to get from reactants to products that has a lower activation energy. They also may force a more favorable orientation of reactant molecules, and enzymes are an example of that. The intermediates or the reactants may be oriented properly to increase collisions that are effective, and they may also be involved in the creation of an intermediate that may or may not introduce a new reaction pathway, but they may help to create a higher concentration of an intermediate, which is going to facilitate a rate of a reaction. We want to be able to distinguish between homogeneous and heterogeneous catalysts, and that simply refers to the phase that they are in relative to the phase of the reacting particles. So if you have a gas phase reaction and you introduce a gaseous catalyst, that's a homogeneous catalyst. It's in the same phase as the reactants. But if there's a gas phase reaction taking place and the catalyst is a solid, that would be considered a heterogeneous catalyst. Here's an example of a heterogeneous catalyst that is operating. We have, first of all, the surface there is representing the platinum that you might find in a catalytic converter. The first step is that the reactant absorbs onto that surface. The second step is that the second reactant, represented by those yellow molecules there, are going to react with that green molecule on the surface, and the surface is effectively orienting one of those molecules, the green one, in a particular way to facilitate the reaction. And it may actually be that both reactant molecules are adsorbed onto the surface in such a way that they've oriented properly, and then they react with each other on the surface. After the reaction takes place, the products are actually desorbed from the surface, and that's part of how a catalytic converter works, is the particles are adsorbed onto platinum metal. Another example that I wanted to give here is that of a homogeneous catalyst operating the way an enzyme works, and you may be familiar with this idea. An enzyme is going to allow substrates to interact by forcing them into a proper orientation. And typically enzymes are considered to be a homogeneous catalyst, although they really do have properties of both homogeneous and heterogeneous catalysts once you start getting into the details of the macromolecules that are involved. But it's important that we understand this as an example of a catalyst. Two other ideas that we need to incorporate into our discussion of catalysts. One is this graph, which shows how a catalyzed pathway has a lower activation energy than an uncatalyzed pathway. And this, of course, would be for a catalyst that speeds up a reaction. That is often a graph that you're asked to consider or produce and understand why this lower activation energy would increase the rate of a reaction. Another important graph to be able to analyze in this context is, again, looking at a Maxwell-Boltzmann distribution and seeing that a lower activation energy effectively means that there's a greater number of particles that actually can have effective collisions. You can see in this case, we're not talking about two different temperatures. Both graphs show the same temperature. However, the one on the right is showing a lower activation energy associated with the presence of a catalyst. So there's a great number of particles that can overcome that threshold. So the threshold is lower. The final condition we're going to consider after temperature, the presence of a catalyst, and concentration is the nature of the reactants. And these are pretty straightforward ideas. Different reactants means a different rate, and different reactants may be that the reactant is in the gas phase instead of the liquid phase, and that means going to be higher kinetic energy, and so it makes sense that we're going to have more effective collisions. Surface area is also going to be incorporated into this category. If something's powdered, then there's a greater surface area for contact with other reactants. And finally, stating the obvious, I think, if you have a completely different chemical like potassium instead of sodium, then that's going to affect the reaction rate because potassium is simply more reactive, right? Its one valence electron is much farther away from the nucleus and is easier to remove. So different reactants, of course, mean a different rate of reaction. So that summarizes our discussion of reactant rates, what factors affect rates, and different types of catalysts.